Okay, so here's where we left off. We have the expression from Kepler's third law that tells us what the mass of the central star is in a solar system. And to calculate this, we need these numbers: pi, we need capital G, the universal gravitational constant, we need the period, and we're going to square that, the period of one of the planets, and we need the distance from the star to that planet, and we're going to cube that quantity. So here's the Earth's period in seconds, and notice that I've expressed this in scientific notation. So what I did was I took the decimal point at the end of the number and counted 1, 2, 3, 4, 5, 6, 7 places, and put the decimal point between the 3 and the 1, and I get this: 3.1536 times 10 to the 7th. This number is the same as the number of decimal places I counted in moving the decimal point over between the 3 and the 1. We're going to do something similar with the radius, the Earth's radius. That's the distance from the Sun to the Earth was, if you recall, 150 billion meters. So we're going to count, starting from where the decimal point is here on the right side. We have 3, 6, 9, 10, 11. So that means 1.5 times 10 to the 11th. This number that you end up with before the times 10 to whatever it is, that number should always be between 1 and 10. So we don't want 15 times 10 to the 10th, and we don't want 0.15 times 10 to the 12th. The 15 times 10 to the 10th, well, that's too cold, and the 0.15 times 10 to the 12th is too hot. We want the one that's just right, which is the number that's between 1 and 10, 1.5. So that's how we get 1.5 times 10 to the 11th meters. As you recall, right, I'm going to write this down as MKS units. Here's what this means. As long as we're measuring distances in meters and masses in kilograms and time in seconds, that's MKS, meters, kilograms, seconds. As long as our measurements are in those units, then this number, capital G, will be 6.67 times 10 to the negative 11. So we're measuring the radius of the Earth in meters. That's why we had to do that conversion, and from kilometers to meters. And then we also converted from years to seconds. We did that so that we would be in the MKS unit system. And then also, if you recall, pi is 3.14 or 3.14159. So I've taken all of these numbers and plugged them into their places in our formula up here. So we have m1 equals, up here we have 4 pi squared, capital G, t squared times r cubed. So now we're going to multiply some of these out and simplify them somewhat. So let's start with 3.14159, and we square that. So we're going to get this. 4 times 9.8696, let's call it. Okay, over, and let's do 3.1536, times 10 to the 7th. Well, the way we handle that on my calculator is we hit the EXP key and then 7. And you can see on the display that it says 3.1536 times 10 to the 7th. And we're going to square that, and then we're going to multiply that by this other number down here, which is 6.67 times 10 to the negative 11. So we do exponent 11 negative. So this says 6.67 times 10 to the negative 11, and I hit equals, and we get this. 663334.43704. Okay, so far, and then now we're going to deal with this thing over here, which is 1.5 times 10 to the 11th, and we're going to cube that. So let's go 1.5 exp 11, and we're going to cube that. Now on my calculator, I've got a y to the x key, and we're going to do to the third power, and that just did not come out right. So let's do it again. 1.5 exp 11, and raise that to the third power. That's much better. 3.375 times 10 to the 33rd power. Look like gnarly numbers, don't they? Okay, so let's go to the next step, M1. Now let's resolve this thing that's inside the square brackets here first. So we're going to say 4 times 9.8696, get that answer, and we'll divide that by 66,334.43704, and we get this. That's a small number, 0.000595.142. And we recall that we're going to be multiplying that by 3.375 times 10 to the 33rd power. So let's do that. Let's multiply. Hopefully you can still see this. We're going to multiply by 3.375 exponent 33. And we get this. You can see the number we get there. M1 is equal to 2.0086 times 10 to the 30th kilograms. Okay, so that's the answer that we get for the mass of the sun. Now, let's compare that to what NASA says. Okay, this is basically what NASA says, that the mass of the sun is 1.989 times 10 to the 30th kilograms. Check it out. Right? That means that we're pretty close on both of those. 1.989 is pretty close to 2.0086. Both exponents are times 10 to the 30th. So using this formula, we were able to get an answer that was pretty close to the actual mass of the sun. So we'll come back and discuss more of this later.